All right, we are finishing up section 8.6 as well as module A. So the last part of this video, we are going to continue our discussion on piecewise defined functions. These are just some miscellaneous topics. All right, the first thing that we want to do is we have evaluated a piecewise defined function. We've also graphed piecewise defined functions. And now we're going to create a piecewise defined function based on some graphs. These are going to be linear piecewise defined functions, so these are all going to be linear equations. And so let's go ahead and see how this works. All right, we're going to start with example A. So for example A, what we want to do is we want to figure out the equation for each one of these piecewise defined parts, okay? So the first thing I'm going to do is, we have our function definition. This is f of x. We want our squiggly brackets. And then we're going to go ahead and figure out each one of these linear functions. You can do this several ways. You can compute the slope and then use point slope form. You can also just use rise over run to find the slope. For this first one, because we do have points on the y-axis for both of our equations, we don't have to use point slope form for either one of these pieces. All right, so let's see here. If we look at the left piece, we want to try to figure out our slope. And so when I look at my slope, remember we want rise over run. And so what we have here is if we're going from this point to this point, I want to know how far up do we go. So starting at the x-axis, we have a rise of 1, 2, 3. And we have a run of, from the bottom point to the top point, how far to the right do we go? We have 1, 2, 3, 4. And so this particular piece has a slope of 3/4. That is going to be my m value. And then my b value is what is the y-intercept, and the y-intercept here is 3. For this piece, we also want to know our restrictions. And so what we have is we use this particular piece if our leftmost value is -4, it is an or equal to statement because it is a solid circle, and then we have less than 3. I'm sorry, not 3, less than 0. Remember that we want the x coordinates, not the y coordinates. And so my x coordinate at that point is 0. All right. And that's the first part of our piecewise defined function. All right, let's come to the second part. The second part, again, we're going to do the same thing. I want to figure out what my slope is. So we're going to do our rise over run. And for this one, to get from our y-intercept down to our x-intercept, we have that we are going down 2 and we are running 3. And so that is going to be a slope of -2/3. My y-intercept, my b value, is 2. And so there's the equation part of our function. And then we want our domain restrictions. And here our domain restrictions is going to be 0 is less than or equal to x is less than or equal to 3. We have both are solid circles. That's why we have the or equal to statements. And then again, remember we want the x values from left to right. When we're on the y-axis, x is 0. and then we go all the way to x equals 3. All right, so that's our first function. All right, now let's go ahead and come to the second one, part B. All right, for part B, this one has 3 pieces. And so we're just going to go ahead and break down each one of these pieces. So again, we're going to start by writing our function name, f of x, and for this one, I'm going to go ahead and start with the easier pieces, and so I'm going to move from right to left. The 2 easy pieces are the right and the middle, and the main reason that they are easier is because they do have y-intercepts. And so we can do these 2 pieces just like we did on the previous example. So let's start with the right piece so that we're not bouncing all over the place. The right piece, again, the first thing that we want is what is the slope. And so to get from our top point to our bottom point, we are going down 2 and we are going right 3. And so our slope is -2/3. X, and our y-intercept is 1, and so we have a b value of 1. All right, for our domain restrictions, we have 0 less than x less than 3. Remember that we want the x values of these points, and so this one we are starting at 0. It is an open circle, and so it is a strict inequality. We are going to 3, and so we also have an open circle, and so that is why we have our less than 3. All right, for our middle piece, again, we want to know what is our slope, and our slope is 3 down, 2 to the right, and so that is -3/2 x, and we have a y-intercept of -3, and so that will be our b value. All right, for our domain restrictions, we have -2 is less than x is less than or equal to 0. All right, so we are starting on our smallest x value, which is -2. We have all of the values between -2 and 0, and because we have a closed circle at 0, we have an or equal to statement. All right, for our third piece, the first part is easy. We still want to know what is our slope. And so our slope is, we are going up 3 and to the right 2. And so our slope is going to be +3/2. And because we don't have a y-intercept for this particular piece, we do need to use point slope form. So just a reminder, point slope form, we have y minus y1 equals m times x minus x1. You can use any point that's on here. I'm going to go ahead and use my x-intercept, -4, 0. And so when we plug this in, we have y minus 0 equals 3/2 times x minus negative 4 becomes a plus 4. All right, so y minus 0, that is just equal to y. And if we distribute the 3 over 2, we get 3 over 2. And if we multiply 3 over 2 times 4, we get 12 over 2, or 6. Okay, so we just want this piece here. We don't care about the y because remember that's my f of x. And so we get 3 over 2x plus 6. And then we want our domain restrictions. For this one, my leftmost point has an x coordinate of negative 4. It is a solid circle, so we're going to use a or equal to statement. And then we are going to the right up to negative 2. And this one also has a closed circle, and so it is also going to be an or equal to statement. All right, so hopefully that helps you have a better understanding of how these piecewise defined functions, how to create them, and gives you a little bit better understanding when it comes to graphing them. All right, the last thing that I want to mention is we want to talk about some special functions in algebra that are technically piecewise defined functions. The first one we've already talked about. It is the absolute value function. And even though we don't write it in piecewise function notation, it is still technically a piecewise defined function. And why is that? Because depending on what our input is, we have different ways that we have to compute it mathematically. So for instance, the absolute value function, if x is less than 0, then we multiply by negative 1 or we change the sign. On the other hand, if x is greater than or equal to 0, we leave it exactly as it is. And that is what a piecewise defined function is depending on what your input is, you do different things. All right, now I'm going to mention another one. We are not going to focus on this, but just to kind of show you another example of a special piecewise defined function. You may see this in your future math classes. We have something called the greatest integer function. And so the greatest integer function is defined as the greatest integer less than or equal to the number. Some people also refer to this as the floor function. And so basically, we're always rounding down. Okay. Our notation is going to be these kind of double square brackets. They're not regular square brackets. Notice that they are kind of doubled up. When x is positive, what we do is we drop the decimals. Now we do have to be careful when x is negative. Remember that we are wanting to round down or we are wanting to round to the left. And so when x is negative, we drop the decimals and we move one space to the left or subtract 1. All right, so now let's go ahead and kind of see what this looks like. We're going to evaluate this and then I'll show you what the graph looks like. Okay, so if we start with f of 5, we want to find the greatest integer that is less than or equal to 5. This is an integer, and so f of 5 is just equal to 5. All right, now let's look at the next one. If f is, we want to find f of 15.276. And so for this, what we do is we're just going to drop the decimal part, and so we get that this is equal to 15. 15 is the largest integer that is less than or equal to 15.276. For the positive numbers, this is pretty easy. Drop the decimals, you're done. Now, when we look at negative numbers, we do want to be careful. Negative 3 is an integer, and so f of negative 3 is equal to negative 3. We don't have any decimals to work with, and so we're done. Now we do have to be careful with something like f of negative 1.296. This is not equal to negative 1. This is actually equal to negative 2. And to kind of visualize this, okay, we have negative 1 here. All right, here's our 0, and here is negative 2. And negative 1.296 is somewhere in the middle here. But remember, we want the integer that is less than or equal to negative 1.296. And so we always round down, or we round to the left, and we get negative 2. All right, so now let's look at what the graph looks like for something like this. All right, I'm going to go ahead and put my tick marks here. Okay, so what this looks like is, let's start with 0. Okay, 0 is an integer, and so it's going to have a closed circle. And basically all the numbers that are greater than or equal to 0 up to and not including 1 are going to round down to 0. Once we get to 1, we need to move up. And so 1, the greatest integer less than or equal to 1 is 1. And so we have a closed circle at 1, 1. And all of the numbers between 1 included and strictly less than 2 round down to 1. And we can continue this pattern when we get to 2. 2 is an integer, and so 2, we're going to have a closed circle. And then all of the numbers between 2 included and strictly less than 3 will round down to 2. All right, I think that's enough to kind of see our pattern. And so we want to kind of repeat this pattern on the left side of our graph. So when we go negative 1, we have a closed circle. And everything to the right of negative 1 and less than 0 will be on this level. All right, we go down to the next one. Negative 2 is an integer. It is equal to negative 2. And everything to the right of it and strictly less than 1 will be on this. And finally, our last piece, negative 3 is an integer. We have our closed circle there. And everything to the right of it, excluding 2, will be at this step. This is, when we talk about what do we call this thing, for instance, absolute value, we call it V-shape. Quadratics, we call them parabolas. Another definition or another way that we explain this is we call this a step function. Okay, this is not going to be a high priority topic, but just to kind of show you another example of a graph of a function that doesn't necessarily look like piecewise, but it is. This is one of them. And this one, notice that we do have a lot of closed circles and open circles. Every single one of these steps has a closed circle and an open circle. All right, that finishes A.6, and that also finishes off Module A. And so I will see you again shortly when we start Module B.